Reflection of mechanical impedance through a gear train. Actually, whenever we have gear in the rotational mechanical system, we are not going to keep the gear. We are going to reflect the impedances to put all the impedances on one shaft for easy dealing with the system. What do I mean by this? If I have this rotational mechanical system with gear, notice that the torque applied here, this is one side of the gear, this is the other side of the gear. Okay, then that inertia with the spring and damper connected to the other side, as you see here. If I want to handle this or find the model of this system, it has been found that it's much easier to take this component all to this shaft. We call it reflection of impedances to the other shaft. Can we reflect the torque and the angle to this shaft? Yes, we can. So either one, you can take all the components or all the elements of rotational mechanical system with gear, put them all on one shaft. That's going to make the development of the transfer function easier. Let us develop the equation of motion here. If I develop the equation of motion for the system given earlier, I can say that j squared plus ds plus k into theta 2 equal to T1 into N2 over N1. Remember, I said T2, if you remember earlier, we said T2 equal to T1 into N2 over N1. So when I go to the other side, when I bring the torque to the other side, that's how we can put it. Now, if I substitute theta 2 with their quantity as well, theta 2 means this value, with their quantity by reflection, as I mentioned earlier, it's going to look like N1 over 2 into theta 1. Now, consider all these terms. We are going to get to this point. What is this? This is the mechanical impedances as they are, and instead of having T2 here at this location, we make it in terms of theta 1. How am I going to get theta T2 in terms of theta 1? We are going to find that T2, as I mentioned earlier, T2 equal to T1 into N2 over N1. So I put it here. So that's how the system will look like. So if I put also the equivalent of theta 2, instead of having theta 2, I will put its equivalent with the same way as discussed earlier. This is going to be the value of theta 2. So notice here, we are going to have theta 1 into N1 over N2 equal to T into N2 over N1. Let us multiply the equation into N1 over N2. I will multiply the equation, this equation all here, into N1 over N2, and the other side into N1 over N2. It will result in, this will cancel this will cancel this, so the remaining will be only T1. And here, N1 over N2 multiplied into N1 over N2 will result in N1 over N2 square into theta 1, and the remaining will be the same. Solve this equation. It's going to be theta 1, as you see here, all theta 1 of S, but N1 over N2 square will be multiplied into all the elements. Of course, here he wants to prove something. We are moving to prove something. So I reach to point where the torque is equal to theta 1 multiplied into K N1 over N2 square plus D N1 over N2 square plus J N1 over N2 square. So now we can redraw the previous system as you see here. It's we are putting the impedances here multiplied into N1 over N2 square. The other one K multiplied into N1 over N2 square, and similarly J into N1 over N2 square. What is this actually? This is actually the same system as before, but the impedances on the lower shaft reflected to the upper shaft. Now, if I want to put rule here so that we can follow it earlier, we are going to find that the impedance can be reflected by multiplying the impedance into the gear ratio, selected or taken as you see here. So the impedance multiplied into the gear ratio square, and you will take the ratio as you see here. Number of teeth of gear on the destination shaft over the number of teeth of the gear on the source shaft. So destination over source. Destination over source. What does it mean here? We will see it in the example of the next slide. So if I consider this example, we have a motor where the motor is connected to this inertia through a gear having N1 and N2. N1 is 50 and N2 is 100. Notice that J is connected to N2. That means its source is N2, or its location is N2. Right now it's on N2. If I want to model it, the easiest way is to bring the inertia to the shaft of the motor. So if I want to move the inertia to the shaft of the motor, the system going to look like this. It's a motor connected to, this is the motor connected to the inertia. Okay, so if the case is like this, that means the inertia is coming to N2. Again, its source is coming to N1. Its source is N2 and it's going to N1. In this case, we are going to multiply the inertia J into N1 over N2 square. So the inertia will be equal to N1 over N2 square, which the destination over the source. Again, destination means the gear, the inertia is going to. Location or source, the location or the gear where the inertia is connected. Find the transfer function theta2 over t1 for the system shown. The system is having few impedances at certain shaft, another impedances at different shaft in rotational mechanical system. The two shafts are linked through a gear which having N1 and N2 number of teeth. So to calculate the transfer function for this kind of system, we need to put all the impedances or all the elements of the system to the same shaft. So we have two options: either take these elements to the upper side or take whatever elements here to the lower side. So what are we going to do here in this example? We are going to do the other choice. We are going to take all these elements to this shaft. How this is going to look like, you will see it in the next slide. Here I am putting the original system to see how the reflection is going to be. So remember, we need to reflect this element to this side, this element to this side, and these two elements to this side. Now, for that, we need to calculate the equivalent damper. Equivalent damper will be equal to D2 as it is, plus the D1 with reflection. Similarly to J is equal to J2 plus J1 with the reflection ratio, multiplied into the reflection ratio, and K equivalent is equal to K2. Theta 2 is the angle at its location. Nothing will happen to it, so it will stay as it is. Now, how about T1? T1, we will bring it to the other side. T1 will change its location. T1 will change its location. For that, when T1 it change the location, we will multiply it into the ratio. The ratio to reflect the torque will be destination over source. Destination means the destination gear over the source gear. So it's equal to N2 over N1 as you can see here. So now we prepare the system which the system is 1 degree of freedom, which needs one equation to describe it. We will see it in the next slide. So here is the equation. It's going to be 1 degree of freedom, as I said. So all the impedances into theta 2 equal to the total torque. Rearrange the equation to find that theta 2 over T1 equal to this transfer function, and here is the shape of a block diagram. Another example. In this example, he said find the transfer function GS equal to theta 2 over T1. So we need to calculate theta 2 here over T1 for the rotational mechanical system given. So what am I going to do here? If you notice, we are going to reflect the elements. So we are going to put all the elements on the same shaft. That's why, or in easy way, we can reflect this impedance to this side. So if I reflect it, it's constant equal to 4. We will multiply it into the destination over the source. Destination gear is 25, source gear is 50. So it's equal to 25 over 50, remember, all square. That means it's equal to 4 into 1 over 4, which equal to 1. That's why here it's equal to 1. And since I'm going to the other side, and you want theta 2 to be in the transfer function, I mean, we express the transfer function in terms of theta 2, we will reflect theta 2. So theta 2 will not stay on its location. Theta 2 here will be taken to this point. So if I take it to that point, we will multiply it into a ratio. The ratio, when I'm reflecting theta, is going to be equal to location or source over destination. Not same as the torque. We are going to do it in opposite way, or its equation is opposite way. If you remember, we discussed it at the beginning when I talk about the theory of gear. So I will put here, let me put it at this location. So the theta at this location, which will be here, will be calculated as theta 2 into 50 over 25. Again, source for the angle, only for the angle, for theta is source over the destination. So once I put the components on this shaft, as you see, we can develop the transfer function. Let us see in the next slide. So here's the system after the reflection. When I look at the system, we are going to find that there are two thetas result of the torque applied. When I apply the torque here, there will be a rotation here, which theta 1. Then theta will remain the same until we cross a spring or damper. Here we have damper. So after the damper is going to be different theta. That means our torque applied going to result in two thetas, theta 1 and theta 2. Here he write it as a theta A, because theta A is nothing but theta 2 reflected. Theta A is theta 2 reflected. So now if I am having here theta, and here another theta, we can apply or write the equation of motion for the system with the same way as before. So as you see, we are having two equations to describe the system. Impedances at theta 1 into theta 1 minus impedances linking theta 2 to theta 1 equal to the total torque applied here into theta A. Theta A is theta 2, but into the ratio. Similarly, here the link, here the impedances at theta 2 or theta A reflected equal to 0, where theta 1 is the angular displacement of 1 kilogram inertia. It's fine. Now we will solve the equation to find the theta A equal to this much. This is the value of theta A. Again, I'm reminding you, theta A is equal to theta 2 multiplied into the ratio. Theta 2 reflected is equal to theta A. Let's see in the next slide. Now, after simplifying the equation given earlier, theta A over T will be written as you see here. Now what is remaining is to find the value of theta A. Remember from earlier discussion, theta A, I will write it here in different way. Theta A equal to theta 2 into N2 over N1, which equal to theta 2 into 50 over 25, which equal to theta 2 into 2. That means theta A can be replaced by 2 theta 2. So here, this one can be replaced by 2 theta 2. When you divide both sides of the equation by 2, it's going to result in theta 2 over t equal to 1 over 2 over this value. So that's how we can develop the transfer function of it. Multiple gear train, what will happen if I'm having a chain of gears? I mean a train of gears, or gear train means gear after gear after gear. It's the same idea, nothing new here. It's the same idea. Let us consider, for example, theta 1, how it's going to look when we are going to different level. If I will look at the value of theta 1 from this shaft to this shaft, how it's going to be? It's going to be equal to theta 1 into n1 over n2. Remember, location over destination. So here it's theta 1 into n1 over n2. Now let us come to this shaft. At this shaft, it's going to be multiplied, or theta, the value of theta 1 at this level will be this value multiplied into the gear ratio, which will be equal to this value, n1 over n2 theta 1, n1 over n2 theta 1 into n3 over n4, n3 over n4 as I mentioned. Similarly, when I come to the second level, it's going to be multiplied into n5 over n6, so n5 over n6. So you will find finally that the reflection of theta on a train of gear or gear train is going to be calculated as theta 4 will be equal to theta 1 multiplied into n1, n3, n5, because this is all considered as a locations over destinations. Location, 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 and here location means source. Destination, destination, destination. So we'll multiply theta 1 into the ratio as shown here. It's going to find its equivalent at different level. Previously, we dealt with a gear system with consideration for the gear to be ideal. When the gear is ideal means does not have inertia and does not have damping effect. In reality, the gear always have damping effect and has inertia. How am I going to deal with the system if it's with a gear and the gear is not ideal? Let us look at this example. It's going to make us clear. The example asked me to calculate theta 1 over t1, theta 1 over t1. So it's very clear that you bring all the elements, all the impedances in the system, and bring them all to this level. How am I going to do so? We have here inertia J5. J5 comes in the same level with J4. Add them and reflect them to this side. Once you are in that side, you will find you are in the same level or in the same shaft with J2 and J3. This one in the same level with J2 and J3. Add them together all. Then reflect it to the second level. When I reflect it to the second level, I will find whatever coming from the bottom will be added to J1. And we are going to reach to the end where J equivalent is equal to the whole quantities given. Similarly, we can do for the damping. For the damper, we can do the same thing. On this shaft, there is no dampers. On this shaft, we have this damper. And on this shaft, we have this damper. So we have D2 and D1. So D2 has no D's to be added to in the same shaft. So we will take it only, take it as it is, and we will reflect it to this shaft. Once I reflect it to this shaft, it will be in the same shaft with D1. So we will add it with D1, and that's going to be D equivalent. In this case, we are getting the system completed. Let's see in the next slide how it's expressed. So this is the result here. This is J equivalent, means reflected, and this is D equivalent, reflected to the shaft of T1 and theta 1. So how the reflection is, we said J equivalent is equal to J1 because it's not reflected, added J2 plus J3 into N2 over N1 square, because these two are to be reflected, plus J4 and J5 reflected twice. So he take the item one by one. What I discussed in the previous slide, I take from one level to the second level, I add and reflect, add and reflect. Here he take each item by itself. J1 is at the shaft of J1. J2 and J3 on the second shaft, so he reflects them by themselves. J4 and 5, they are in the same shaft, they are added and reflected twice, finish. And the equivalent, as I discussed earlier. So once we finish, we reach to this stage, we have J equivalent and D equivalent. We can write the inertia as the equation of motion as seen here, rearrange it to get the transfer function, and this is going to be the transfer function, which is going to be in this format of a block diagram. That's all about rotational mechanical system and rotational mechanical system with gear. I hope everything is clear. I wish you all the best. Thank you.